Now let us do some problem sets. And these problem sets from 1 to 5 are modeled to be answered in a few minutes. So question number 1, if y hat is equal to 3x plus 5 and x is equal to 4, by how much does y equals 19 deviate from y hat on the line? So how do we solve that? We just substitute x equals to 4 for this x here, and y hat is equal to 3 times 4 plus 5, so that's equal to 17. Notice that this value of your y hat deviates from y equals 19 by positive 2 units, right? So our y is deviating by positive 2 units from this y hat. Question number 2, if y hat equals 3x plus 5 and x is equal to 6, by how much does y equals 20 deviate from y hat on the line? So the same solution, our y hat is equal to 3 times 6 plus 5, this is 18 plus 5, this is equal to 23, and it deviates uh, by positive 3 from the y equals 20, and y equals 20 deviate from this by negative 3 units, so negative 3. Question number 3. Find the sum of the squares of the residuals. If the residuals are 3, negative 1, negative 4, and 2. So we could pretty much involve, a table here. And if this is my box, I will have to write 1, 2, 3, 4. So 4 lines, horizontal lines, 1, 2, 3, 4. And my values are 3, negative 1, negative 4, and 2. And the square of these residuals are 9, 16, or rather 9, 1, 16, and 4. And taking the summation of these residuals, S is res, is just equal to, what is the answer here? 9 plus 1 is 10 plus 20, so this is 30. Okay, the answer is 30. How can you tell from the correlation coefficient that a function fits the graph or the data perfectly? Now if your R, because the correlation coefficient indicates the strength of the correlation between the variables, when your R is equal to 1, that means that the given data fits perfectly the function, meaning that the function, the data points when graph or when plot on a certain Cartesian coordinate also yields the same straight line as when they are taken into equation. So the points when connected together form a straight line, and so the equation also is very much indeed perfect to the data points. And this R is equal to 1 is applicable for those points that fits perfectly in a positive uh, direction. So the slope is positive, and if the slope is negative, then R is equal to negative 1, and the data points will form or will define a line which is decreasingly negative, or the slope is negative. Okay, so when your R is equal to 1 or negative 1. Question number 5, what kind of function has the multiply property? This is for exponential functions, right? So we have taken this already. And if you do have a pattern of Multiply, that's just exponential function. No. Uh, Wait, this is not exponential. This is for power functions. Exponential function is add multiply. And multiply add the inverse of exponential, which is logarithmic. Question 6. For what kind of function could fx plus 3 is equal to 8fx? So as you can see here, this is an addition property. So we add 3 to the x, and here we multiply 8 to the fx. So it's multiplication. So this is most likely an exponential function, right? Because we have the property add multiply to its exponential functions. Question number 7. This is a review of the last chapter. Log 5 plus log 7 is just log of. This is just log of 5 times 7, or 7 times 5. It's equal to log of 35. Question number 8. What is the least common denominator for 2, 7 plus 3, 8? The least common is actually 56, right? So you could do it like 16 or 56 by multiplying by the denominator of each term. So we have 21 over 56. So this is the least common denominator. In a right triangle, opposite leg over adjacent leg is the opposite over adjacent. This is the tangent, right? Tangent of the angle. So remember SOHCAHTOA, tangent is opposite over adjacent. We take it from here. Expand the square mx plus b square. So to expand this square, we could actually write two factors of the same binomial term. So mx plus b times mx plus b. That should be equal to m square x square plus you have 2 bmx, so 2bmx plus b square. Okay, so this is the answer for question number 10. And we have some answers here actually. Okay. Now we go to the exercises on residuals. So residual problem number 1. Suppose that this data have been measured for two related variables x and y. So these are our x's and these are our y's. Okay? So when x is equal to 5, your y is 11, x 8, y 16, 11, 19, 14, 27, 17, 25, 20, 29, 23, 33, 26, 42, 29, 44, 32, 51. Letter A. Enter the data into list on your grapher. Show by linear regression that the best fitting linear function is y hat is equal to 1.4x plus 3.8. So you're graphing, the answer here is, if of course we must have this grapher. If we don't have a grapher, then the thing that we could do is to do it by statistical data or statistical analysis. But that will take us quite a long time. Okay, so if we have a grapher or a graphing calculator, the graphing calculator will give us this value. Y equals 1.4x plus 3.x for the regression line with the correlation coefficient at 0.9842. Okay. Number two, make a scatter plot of the data on your grapher. On the same screen, plot y hat. How well does the linear function fit the data? So we don't need to do it manually. And in your grapher, you should be able to obtain this for letter B. Okay? So extending from a 30 by 40 window, you could see the plots of the points. So this is the first point, 511. We have 816, 1119, 1427. This is for 1725, 2029, 2333, 2642, 2944, and 3251. This is your best fit line. And the line fits the data well. Okay, this is the best fit regression line. Letter C, calculate x or the means x and y, the averages of x and y. Show algebraically that the average point x, y is on the regression line. So how do we do this? Okay, to compute for our, okay, we're going to compute, make a tabulation of our x and y. So how do we do this? First, to get our x, let us take note that our n is equal to what is the number of our data? X is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is equal to 10. Okay? Now let us compute for the x's, the average of x. X average is equal to the summation of all x's divided by n, right? So in this case, we go to this table. Let us compute for x, and let us put our values of x, which is 5 plus 8 plus 11 plus 14 plus 17 plus 20 plus 23 plus 26 plus 29 plus 32. That gives us 185. So this is 185 divided by n, which is equal to 10. Therefore, our x bar, or the mean, is equal to 18.5. Am I correct? Now let's compute for our mean for y, okay? So let's compute for y. This is equal to the summation of all the y values over n. So that should give us, our y is 11 plus 16 plus 19 plus 27 plus 25 plus 29 plus 33 plus 42 plus 44 plus 51. This will give us 297. So this is 297 divided by 10. So our y bar, or the mean, is equal to 29.7, right? Okay. Show algebraically that the average point xy is on the regression line. Now let's take a note. What is our regression line here? Our regression line, taken from the grapher, is this. So y equals 1.4x plus 3.8. Y equals 1.4, this is our regression line, x plus 3.8. Okay. Now let us have the line of the y bar and the x bar. Okay, so let us see that. Suppose that our y, or our x rather, is 18.5. So our y hat of 18.5, or this is f of 18.5, will be equal to 1.4 times 18.5 plus 3.8. And this is equal to, let us compute, 1.4 times 18.5 plus 3.8. This is equal to 29.7. So as you could see, this value of x, the x mean, okay, the x mean, y mean is therefore on this regression line, because using the mean 18.5 and substituting it to the given regression line gives us 18.5 and the value of our mean for y, so 29.7. So the average 18 x average and y average therefore exists on the regression line. So define new list to help you calculate the squares of the deviations. Y minus y bar square and the squares of the residuals. Y minus y hat square. By summing this list, calculate SS def and SS res. So in here we are going to make tabular comparisons for our deviations and residuals. So we need to add, okay, lines here. Okay, so these are our lines. Okay. Now we have to make 4 tables. Let me move this. Okay. So the first one will be for y minus y bar. This is for the mean. And this is for the residual. Okay. This is for the squares of the means. And this is for the squares of the residuals. The square of the deviation from the mean and square of the residuals. So these are our y's, okay? These are our y values. Our mean is y is equal to 29.7 based on this computation, 29.7. And our y bar, or y hat, is 1.4x plus 3.8. Our y hat is 1.4x plus 3.8. Okay? Now to solve for this, you could do it using the calculator, but what I'm going to write here are the values already. So y minus mean is 11 minus 29.7. This is negative 18.7. This is negative 13.7. This is negative 10.7. This is negative 2.7. This is negative 4.7. This is negative 0.7. This is 3.3. This is 12.3. This is 14.3. This is 21.3. For y minus y hat, first you have to get the y hat for every of the x. For every x values. So x5, get your y hat from here. So if x is equal to 5, this is 1.4 times 5 plus 3.8. And this is your y hat. So anyway, these are our summary for y hat. We have or y minus y hat. We have 0.2, we have 1.0, negative 0.2, 3.6, negative 2.6, negative 2.8, negative 3.0, 1.8, negative 0.4, and 2.4. Okay? For instance, this would be, let me compute this for a while. That's 1.4 times 5 equals 7 plus 3.8 equals 10.8 minus your y, which is 11, or 11 minus 0.11 minus 10.8, that's equal to 0.2. That's why we have 0.2 here. Okay, and so on and so forth. Now the squares of my deviations are, these are the squares. So if you square this, it will give you 349.69. This is 187.69, 114.49, 7.29, 22.09, 0.49, 10.89, 151.29, 204.49, and 453.69. Now these are the squares for my y minus y hat square. That's 0.04, 1.00, 0.04, 12.96, 6.76, 7.84, 9.00, 3.24, 0.16, and 5.76. Now we have to get the sum of the squares of the residuals, or the SS res. So the sum is equal to SS res, and this is equal to, what is this equal to? This is equal to 46.80, right? Now for this portion here, this is the summation is equal to the SS dev. And SS dev is equal to, what is my SS dev? 1502.10. Now we're going to solve for our coefficient of determination. And to solve for our coefficient of determination, we need a space. So this is our space. And we know that our SS dev is 1502.10. SS res is 46.80. So our R square is equal to SS dev minus SS res divided by SS dev. So our R square is equal to, what is SS dev? 150.2.10 minus 46.80 divided by 1502.10, and this will give us a coefficient of determination which is equal to 0.9688. Okay? Now why do we need to get the positive square root? Notice that your data is increasing, right? So from 5 it goes to 32 and it's increasing, and the value of your y is also increasing. So therefore we will get the positive square root to get our, this is our coefficient, correlation, coefficient of determination. To get our correlation coefficient, we take the positive square root of our r square. So r is positive square root of r square. And positive because our data is increasing. Okay? And the coefficient of correlation is 0.9842, which agrees very well with part A. Okay? Look at them. They have a very strong correlation. And this strong relation among the variables is given by this correlation coefficient 0.9842. And taken manually, we confirm that our coefficient of correlation is 0.9842. Okay? So that is for letter D. Letter E, the line y2 equals 1.5x plus 1.95 also contains the average point. So there are two lines now. We have the y hat, the first regression line, which is 1.4x plus 3.8. Now we have another line. And this line also, what do you call this? Professes to have the average point, x bar, y bar. So 1.5x plus 1.95. So it has a slope of 1.5 instead of 1.4. So look at this. This is a greater slope than this original y hat. Plot the line the same screen as in part B, and can you tell from the graph which line fits the data better? Let's see. Now this is the graph of this equation, y equals 1.5x plus 1.95. And plotting it on the same screen as the original y1, 1.4x plus 3.8. This is 1.4x plus 3.8, the one in broken line. So this line. Okay? And our y equals 1.5x plus 1.95 is this. Okay? So as you can see, it is hard to explain. It's hard to tell which line fits the data better. So because it's hard to do that, we are going to have the competition of which regression line is much better by computing for the SS-res of this new line. Okay, because as we said, the one which yields the minimum SS-res will be the better regression line. So therefore, we are going to create a table. Again, we're going to create a table and look for the SS-res. So let's do that. Okay, because it's very inconvenient for now to write all of the numbers, so I'm going to present to you the table now. So this is our y hat. This is our new y hat when our slope is 1.5x. This is y minus y hat now, okay? Our y is the same as the table, or as this. So this is our original data. this data, okay? And our y minus y hat would now be this, okay? And our y minus y hat square is equal to this. Now look at this SS res. So the SS res is just computing this square of the residuals. So SS res is equal to the summation of all the values on this column. And in this case, this will give us 54.2250, which is also indicated here, which is larger than SS res for the regression line. Therefore, the better fitting line is the regression line, y equals 1.4x plus 3.8, because it has a lower regression, or it has a lower sum of the squares of the residuals. And the sum of the squares of the residuals of that is, we have 46.80 only, right? Whereas the square of the residual of the new line, of this new line, is 54.2250, which is much larger than this. Okay? So this is the solution for residual problem number 1. Thank you for watching.